Uh, I think we should wait for a little bit time more, maybe, right? What's the time now? Let me watch.
Now it's exactly 1 p.m. Yeah.
Yeah, it's exactly 1 p.m. Where did you start? No, you started like 5 after yesterday, right?
Maybe a couple of minutes.
A couple of minutes.
I honestly don't remember.
Yeah, I think we can wait for a couple more minutes.
Yeah, sure.
Yeah. Anyways, welcome everyone. Good morning, good afternoon, good evening, depending on where you are. Thanks for joining for Giacomo's class again today, and we are looking forward to his very cool lectures. That's all I have to say. So Giacomo, take it away.
Yeah. Morning, everyone. Give me one technical thing. So can you make? I can't share my screen because let me send you a message. I'm using a different device. I'm using a different device to share my screen. That's what I forgot to mention. I tried to be fancy this time, so I have an iPad with the slides to write on, and then there's a camera in front of me.
I hope you know I've earned the right to share something, Giacomo.
Yeah.
I hope so.
No.
No. Still no.
Did you see the message that I sent you?
Sorry.
Actually, okay, that's good because there's still people trickling in, so I'm still admitting.
Yes, I will do it. So I need to find the right person.
Okay, so in the meantime, I put so yesterday's slides are already on my website, and I'll do the same. I'll do the same with today's material, but I prefer to do it just after the class, just to make sure if there are typos or other things. Because sometimes going through the material, I notice things and then I fix that. Okay, so. Okay.
All right.
So what I would like to do today, again, there are we're gonna have 2 sessions today. I'll take breaks after about every hour. And the general plan that we're following is that we're trying to build up so that eventually in the last class, we can talk about recent research on quantum optimization. And so to be able to do that, we're still building up tools. In fact, this morning for me, I guess, this afternoon, Paris time, early afternoon, Paris time, I want to discuss another fundamental problem for quantum computers that's called Hamiltonian simulation. And it's essentially the problem of simulating the dynamics of a quantum system. And this one is particularly important because it comes up for 2 things that are relevant for optimization. One is the solution of linear systems, and the other one is the computation of Gibbs states, which sounds like a fancy word, but what it means for optimizers is that something that's useful to compute positive semi-definite matrices. And let's say, trace inner products between matrices. So it's relevant to several areas of continuous optimization. And then finally, in the second part of the class today, I'll give an overview, mostly of research on continuous optimization, but also some research in discrete optimization. Okay, so I don't have many slides for the first part of the class because the material is requires a bit of care. So we'll go very slowly, and just as yesterday, or feel free to ask questions at any time. There's really I left plenty of time for questions. So if there's something it's not clear or something you want to discuss further, absolutely don't worry about just raising your hand or asking directly. But please don't use the chat because I don't read the chat during the class. Too many things to look at. Okay, so let's first define the problem that I want to look at. And in fact, for this problem, we're not going to discuss any algorithms. The algorithms are too intricate to discuss given the limited time. But I at least want to give an overview of some of the basic techniques and what type of results we can hope to achieve. And so there is a fundamental problem in quantum mechanics. In fact, this is the problem for which quantum computers were initially proposed. And it's a problem called Hamiltonian simulation. And in this problem, you want to do the following thing. So somebody gives you some Hermitian matrix, A, and some duration parameter, T. It's just think of it as a time length. And you also have some precision parameter, epsilon. And what we want to do is to give an implementation of this matrix exponential, e to the minus iat. So what does it mean to give an implementation of this? I want to construct a quantum circuit, and we know that a quantum circuit is just a unitary matrix, such that this unitary matrix approximately implements the matrix exponential. And this allows me to apply this matrix exponential onto some desired quantum state. So for example, if I want to compute e to the minus AIT applied to some quantum state psi, I know that this is going to be approximately equal to the circuit that we construct applied onto the state psi. Okay. And of course, here there is a notion of approximation. We're not going to be able to do this exactly, but we just find something which is in some norm, it's epsilon accurate. Now, this problem is fundamental for quantum mechanics because even though, as I said at the very beginning, I don't know quantum physics, but the evolution of a quantum mechanical system is governed exactly by this type of equation. So if you have a quantum mechanical system, this quantum mechanical system is characterized by a Hamiltonian. And then if you look at the Schrödinger equation, it tells you that the evolution of the system in time looks exactly like this matrix exponential. So T here tells you for how long you want to simulate your quantum mechanical system. And then this is exactly what you need to compute. Okay. Any questions so far? Okay, so just as a reminder, because I suspect there's some of you that may not have seen this in a while. So what is a matrix exponential? So if I write something like this, you should really think of this in terms of the power series for the exponential. And so it's an infinite series of terms that contains powers of a matrix. And of course, this looks fairly ugly, but there are many cases in which this expression can be simplified. For example, if the matrix is diagonalizable, then things get easier. And this problem is really fundamental for quantum computers. As I mentioned, it's the problem for which quantum computers were initially proposed by Richard Feynman. It's also a problem that is complete for the class of problems that can be efficiently solved by a quantum computer. And so I will mention this now, but we're not going to discuss these aspects of computational complexity anymore in the course. But so for those of you who are a bit more familiar with computational complexity, there is a class of problems. It's the class of problems that can be solved with bounded error in quantum polynomial time. So what does this mean? This is the quantum equivalent of the class P. So these are problems that you can solve in polynomial time with a quantum computer. Now, because with a quantum computer, whenever you do computations, it's extremely rare that you can solve things deterministically, but you can solve things with good probability. And so there is this concept of bounded error, and this means that we want to solve a problem with some good probability. In particular, let's just say that we want to solve a problem with probability at least 2/3, or you could pick, whatever constant you like, with probability 90%, it would be equivalent. So this is a class of problems that you can solve with high probability with a quantum computer in polynomial time. And this problem of Hamiltonian simulation is complete for the class. What does that mean is that any problem in that class can be reduced to this problem. So if you could solve Hamiltonian, if you can, any problem that can be solved efficiently with a quantum computer can be cast into a Hamiltonian simulation problem. Any questions so far? Okay. So we're saying this is an important class of problems. In fact, it represents everything that you can solve efficiently with a quantum computer. And we will see that this has several applications. In fact, the two applications that we'll discuss in the class today are the solution of linear systems and the computation of Gibbs states, which, as I mentioned, is relevant for the computation of let's say, doing some operations on positive definite matrices. So here are some facts on Hamiltonian simulation. So the complexity of the problem, so how hard is this problem going to be, depends notably on two things. So it depends on the matrix that you're putting in the exponent, and it depends on the time duration of the simulation. In particular, the longer the time interval, the harder this is going to be. Which is fairly reasonable if you think of this in terms of you're simulating the evolution of a quantum mechanical system. If you want to simulate the system for longer time, it will be more complicated. And in terms of efficiency, we didn't quite require what does it mean to have an efficient algorithm for this problem. So we need to pick what is the size of the space that we're acting on. So just to fix ideas, we're going to have this matrix A that acts on n qubits, and this means that A is going to be 2 to the n by 2 to the n matrix. Okay. And if an algorithm is efficient for this problem, if it runs in time that is polynomial in n, the time duration n1/epsilon. So what I'm saying here is that, remember, so this matrix has size which is exponential in n, but I want my running time to be polynomial in n, right? So this is logarithmic in the size of the matrix, which is sort of what you generally do in the quantum world. If you have n qubits, these n qubits correspond to a state space that has size, which is 2 to the n dimensional, but I still want algorithms that run in time polynomial in n. And I should mention that, of course, if you can do something which is efficient for some time duration t, then if you just want to change your time duration by some factor, which is still polynomial in the input size, it obviously does not change the complexity. So in general, as long as the time duration is of reasonable size, then you can enlarge the time duration or shrink it a little bit, and it's not going to make too much more difficult, as long as the size increase of the time duration is polynomial size. And there are many different ways to perform Hamiltonian simulation. In particular, what I'm interested in here is talk about the input models, because in fact there are many ways in which you can specify the problem, and this has an impact on the running time of the algorithms. It also has an impact for us because if you're trying to construct algorithms that use Hamiltonian simulation as a building block, you need to know how the data is specified, because this has direct impact on the running time, especially if you think of a situation where you want to solve a problem, which is, let's say, a classical problem. Somebody gives you some optimization problem. You have the data written somewhere on your hard drive, and you want to construct a quantum algorithm to solve that problem. Then you need to know how to translate that data into some form which is digestible for the quantum algorithms that you will use to solve the problem. So the input model is particularly relevant whenever you're trying to use quantum algorithms to solve problems that are classically specified. Any questions so far? So I want to discuss two input models. So the first input model that I want to discuss is generally called the sparse oracle input model. And this model is very similar to what is used for classical representation of sparse matrices. If you're familiar with specifying data for either sparse linear algebra software packages or even integer programming solvers, what you generally specify if you want to describe a problem is that you're going to have a constraint matrix or some matrix on which you want to apply some linear algebra subroutine, and you specify the location of the non-zero elements in the matrix, and you specify the value of the non-zero elements in the matrix. And this model is the direct quantum equivalent of this classical representation for sparse data. So if you want to describe a matrix A, the Hamiltonian, I should have mentioned this. There is this terminology in the quantum mechanical world of a Hamiltonian is a matrix that describes, let's say, the evolution of a quantum mechanical system. Now, normally Hamiltonians are denoted H by H. However, H is also the letter used for the Hadamard gate. And so just to avoid confusion, I'm using A here rather than H everywhere. But generally, whenever you read papers, Hamiltonians are going to be denoted by H. Okay, so how do you specify a Hamiltonian? As I said, similarly to what you would do classically to describe a sparse matrix, you need to give the algorithm access to the location of the non-zero elements, and you need to give the algorithm the value of these non-zero elements. So in particular, you describe a matrix with two maps. So there is a first map that takes, actually, let me do this slowly. So that takes two inputs. The first input is the index of a column of the matrix. That's going to be J. And then, and the second index is the is, let's say, it's the index of the non-zero element in that column. And in particular, if I give to this subroutine the index j and the index l as input, that means that I want to know what is the position of the lth non-zero element in column j. Okay, so you take a column, there's going to be some non-zero elements, and then you need to be able to tell me what is the location of the second non-zero element in this column, and so on and so forth. Okay, and for all these indices, you should be able to give a description in the usual binary representation of integers. Think of your column is going to be number from 0 up to the number of rows, and then you represent these integers as binary strings, and you just should be able to do that. And then, so this tells me the location of the non-zero elements. And then the second thing that you should be able to do is to specify the values of these non-zero elements. Okay, and so to specify the value of the non-zero elements, you need to be able to provide a map that does the following. So it takes as input some column index, some row index in this case, some column index, okay, and then there's going to be some output register, which you can think of this register as being initialized in the 0 state, but we should still provide an implementation in case it's initialized to whatever number there is there. And what this second subroutine should do is that it should spit out in the output register the value of the element in position j and k of the matrix. Any questions so far? So this is really the most direct quantum equivalent of the sparse description of classical matrices. Now, the input model, as I mentioned, is relevant for the running time. In particular, whenever you use algorithms that use this for Hamiltonian simulation that use this input model, then generally the running time of the algorithms scales with the maximum number of non-zero elements in each column or row of the matrix. Okay, so the sparser the matrix is, the faster the algorithm is going to be. In particular, in the worst case, if your matrix is fully dense, then this algorithm is actually not going to have a polynomial time anymore, because your matrix is exponential size, and the sparsity of the matrix will show up directly in the running time. So in general, with this input model, you're going to have efficient simulation only if your matrix is very sparse. I'll give some mention of the running time of this algorithm later on. So what is the general idea to perform Hamiltonian simulation with this input model? So the details are quite intricate, but at a high level, the idea here is to decompose the problem into a simulation of several terms. So in particular, we split the Hamiltonian into a diagonal part and several off diagonal terms. So let's say you have a matrix. So everything is the diagonal is going to go into one single term, this a diag, and then you're going to pick some off diagonal elements, and this will be some off diagonal term, let's say a bar 1. Then you're going to pick some other ones. This will be the off-diagonal matrix A2, and so on and so forth. So you partition your matrix elements into several matrices, such as if you add all these matrices together, you recover the original one. And one of these terms will contain all the diagonal elements. Other terms will contain off-diagonal elements. And then one thing to notice is that if you do this decomposition, then the number of terms in the decomposition is going to be at most the maximum number of non-zero elements in a row or column. Okay, because clearly one way of doing this decomposition is that you take each column of the matrix goes into its own set of the partition. So in the worst case, I can just put every column into a separate submatrix A bar J, and so at most I'm going to have a number of these matrices which is equal to the number of non-zero elements, let's say in a row of the matrix. Okay, and then the reason we do this is that then we're going to decompose the simulation of A. Notice A is the summation of terms, okay? But A appears in an exponent. And so the idea is to split the simulation of A into a product of simulation of these smaller terms. So in particular, I would like to do something like this. Actually, I need to put some brackets otherwise. I would like to do something like this. Okay, where initially I have a summation of terms in the exponent, and then I split this into a product of matrix exponentials. So why would this be advantageous? This would be advantageous because initially I have to compute a matrix exponential for the matrix A1 plus A2, but on the right-hand side, I'm only computing matrix exponential of the matrix A1, and then independently, I'm computing matrix exponential for the matrix A2, and then I just, put this circuit next to each other in a sequence. And so because these matrices are smaller, it gives me hope that I can come up with a simpler simulation algorithm for them. These are smaller and sparser. However, there is no equality here in general. Okay, so you have equality between these two things only if the matrices commute. Otherwise, it's not true. That's an unfortunate consequence of the fact that matrices in general don't commute. Matrix product. But so that's still the general idea that we would like to follow. And so I mentioned again, at a high level, what these algorithms try to do is that they still try to do something like this, but we have to do something a little bit more involved. And in particular, we use something which is generally called a product formula, of which there are many types. But to give you an idea of what a product formula looks like, it looks something like this. So you start with the problem of simulating a matrix exponential of a summation of terms, and you express it as a product of terms. But what you can see here is that I cannot just express it as a product of two terms. In fact, I need, if I want equality, I express this product as a, I need to take the limit where the number of terms in this product goes to infinity. But of course, if I want to have this equality be true only up to some error epsilon, rather than being, some exact equality, if I'm fine with some approximation error epsilon, then the number of terms, when I go from simulating summation of matrices to product of matrix exponentials, then the number of terms becomes finite. So once I know what error I want to achieve, I can truncate this expression here so that I only need some finite h. And there's other forms of this product formula. I'm just giving you one of the most standard ones. Any question on this? Okay. So this is one of the possible input models, and I mentioned this is a very natural model for classical people, in the sense that you're just specifying the location of the non-zero elements in your matrix and the value of these elements. Now, there's another very recent approach to Hamiltonian simulation. This is the one for which I'm giving more precise running time expression, because this model is more general and it essentially subsumes every previous result in Hamiltonian simulation. There are small differences, but up to very small differences, it subsumes everything that we knew about Hamiltonian simulation. And this model also is fairly easy to understand from a classical perspective. So the model works as follows. So remember here, we're trying to simulate some matrix exponential e to the minus ia times some scalar t. Okay, this is what we want to do. And somebody needs to specify this matrix A. So in the previous case, we said, why don't you just give me the list of the non-zero elements and the values of the non-zero elements of the matrix? In the second model, we'll do something different. In the second model, we'll say, why don't you give me some unitary matrix? Remember, unitary matrix means circuit. So why don't you just give me some unitary matrix for which A is embedded in the top left of the unitary? Okay. So in particular, for example, if my A matrix is the matrix 0, 1, 1, 0, then some matrix like this, and then let's say I have zeros here. Something like this will be such a suitable representation for the matrix. So any unitary matrix that has the matrix A that I want in the top left corner, and I don't care what is in the rest of the matrix. This is called a block encoding. As I mentioned, these are fairly new results. Okay, this is an idea that I think the first mentions of this are from maybe 4 years ago, and then the most important published results are from just a couple of years ago. Now, if you do this, so if you try to embed your matrix A into some unitary matrix, you need to allow for some scaling factor, which we'll call alpha. Why is that? Well, the reason is that, so we require that U is a unitary matrix, okay? And A could be any matrix. But in order to ensure that you can embed any matrix in the top left corner of a unitary matrix, you need to allow rescaling down the original matrix. For example, one reason for this is that every unitary matrix has eigenvalues, all of which have modulus 1. So if your matrix A has large eigenvalues, you need to scale it down somehow. So in general, we will allow rescaling down the matrix A so that it can be embedded into a unitary. And when I say give a unitary, what I really mean is, provide a quantum circuit that implements this unitary matrix such that in the top left corner, you can find the matrix A that I want to simulate with Hamiltonian simulation. Okay. Any question on this? So the scaling factor is important. The scaling factor will appear directly in the running time. And you can think of this in the following way. So if I have a unitary that implements directly my matrix A in the top left corner, then things are easy. But if my unitary implements a scaled down version of the matrix A, what I want to obtain in the output is still the matrix exponential for A, not for the scaled version. So I want to compute e to the minus iat. I do not want to compute e to the minus ia over alpha t in general, okay? So if the scaling factor alpha is large, I may have to, in some sense, amplify the signal in the output of the algorithm just to make sure that my output corresponds to what I really wanted to do initially, not to the scaled down version. And so as I was saying, the running time of the algorithm is going to depend directly on this scaled down parameter alpha. So in particular, if you can construct a block encoding U of some matrix A, and the normalization factor is alpha, you can implement the matrix exponential e to the minus iat using a number of gates that scales as alpha times t plus some factor that depends on the error and that scales logarithmically with the error. So this is very good. The fact that your error depends logarithmically in 1 over epsilon is great. It means that you can, get a very precise simulation, so computation of the matrix exponential with very little extra cost. And the first term tells you that, the duration of the simulation impacts directly running time, but also the scaling factor. However, something that is important to note here is that, once again, the dimension of the matrices is not appearing in this running time, okay? So this is my running time expression. The dimension of the matrices is not directly appearing in this expression. So I can simulate a matrix exponential with this running time, but this running time, as is specified in this slide here, it's telling you how many times I'm going to have to apply the block encoding U. So how many times do I have to apply the circuit that contains the matrix that I want to simulate in the upper left corner? So in particular, if I want to, the size of the matrix A might appear in the running time whenever you apply U. So the construction of the circuit U that implements this matrix A might depend on the size of A. But in terms of the running time of the algorithm that computes the matrix exponential using the circuit U as a black box, then the dimension of the problem does not enter into the running time expression in that case. Whereas classically, there's no way to compute matrix exponentials without looking at the dimension of the matrix. Any question on this? It's a very quiet morning. Okay. So these are some preliminaries in Hamiltonian simulation. As I mentioned, I'm not going to discuss algorithms for this. But what I wanted to emphasize is the fact that you can obtain these running time expressions that do not directly depend on the size of the matrix, but they will depend on the scaling parameter if you're using a block encoding framework, or they will depend on the sparsity of the matrix if you're using the sparse access model that we discussed earlier. And then what I want to use these algorithms for is the solution of linear systems. So this will take us most of the first class today. And okay. And the reason I want to discuss quantum algorithms for linear systems is well, there are many reasons. So the first reason is that linear systems are ubiquitous in optimization. There's so many optimization algorithms that just solve linear systems over and over again. And so it seems like it would be a useful subroutine or tool to have in your arsenal if you're trying to come up with an algorithm for a problem. And second, it's because it's one of these areas where the trade-offs of quantum computers become evident. So in principle, if one looks at quantum linear systems algorithms on the surface, it might appear that they give you an exponential speedup compared to classical algorithms with respect to the size of the matrix, which sounds amazing, except that's not really what happens. So in particular, even though the running time expression by itself does not contain the size, so it's exponentially faster compared to the size of the matrix with respect to the size of the matrix compared to classical algorithms. If you take all the details into account, in fact, these algorithms are not exponentially faster unless certain assumptions are satisfied. And so it's important to understand what these assumptions are. And also, this algorithm is a very good showcase of several powerful techniques for the construction of quantum algorithms. So I think they make for very good educational tool. And so, okay, so what we're going to do for most of the class today is to construct an algorithm for a linear system and understand how that works and what are its limitations. So in particular, the construction that I give is based on the seminal work of Harrow, Acidin, and Lloyd. It's the first quantum algorithm for linear system. Now, this algorithm is not the fastest algorithm. In particular, this has been improved, several times in the following. It has been significantly improved, in fact. So when discussing running time, I'll try to give you some more recent results than the original paper. But I think the idea of the original paper is the easiest one to understand, and it's an important building block to see also how the other papers work. Okay, so first of all, let me define, what does it even mean to solve a linear system on a quantum computer? And it will mean the following thing. So first, I need just one definition. I need to define what is the natural quantum representation of a vector. And so We will call this amplitude encoding, and it will be just the most natural representation you can think of. If I have a vector x, I just put it in a quantum state in the following way. So x1, x2, x3, up to x, 2 to the n. So this will be my quantum state. Okay. But remember that quantum states have to be normalized. You always have this normalization condition. And that's why in this definition here, I am dividing all the elements by the norm of x. This ensures that the entire vector is a valid quantum state because it's a unit vector. Okay. So whenever I have some vector, if you see me, if I write a vector between brackets, what this means is really this thing over here. Modular normalization. And so the definition of the problem that we're trying to solve is the following. So somebody gives me some matrix A. I'm assuming it's a invertible matrix, and I'm assuming it's Hermitian. We'll see later on how to drop the assumption that it is Hermitian. And then somebody gives me also some vector B and some precision parameter. And what I want to compute is some quantum state over n qubits. Why over n qubits? Because this matrix is of size 2 to the n times 2 to the n. Okay. And so I want to compute some quantum state psi, which is approximately equal to the amplitude encoding of the solution of the linear system AX equal B. Okay. So what is this thing? This is simply the vector that has the first component of A minus 1B in its first position, second component, and so on and so forth. So it's just the vector that contains the solution normalized. Okay. So here there has to be some normalization factor. Is that clear what we're trying to do here?
So the solution will be the coefficients of the state psi, right?
That's right. Yeah, exactly.
Okay.
Yes.
Okay,
Yes.
thanks.
Yeah. So you take your solution vector, you put them, you stack them one on top of the other as the coefficients of the quantum state. You need to normalize because this needs to be a unit vector. That's what you want to construct. And you want to do this up to some precision epsilon. Okay. So to solve this, we'll have to make some assumptions. And we'll see that some of the assumptions can be a little bit tricky. But so the first assumption is easy. We're going to assume that the input data is described in some suitable way. What does it mean, some suitable way? Well, here are some models that make sense here. The right-hand side vector should be described by some circuit. Actually, let me write it. There should be some quantum circuit that prepares the encoding of the right-hand side vector B. And for PA, the input model could be any one of the input models that we discussed earlier for Hamiltonian simulation, because the algorithm will be based on Hamiltonian simulation. So the matrix A could be described by giving the location and values of the non-zero elements, or it could be described by giving a block encoding. But we're also assuming that we know an upper bound on the condition number of the matrix. This is going to be necessary for the algorithm. And in fact, we'll see that the running time of the algorithm depends on the condition number of the matrix. So as input, somebody needs to tell you the condition number or some value which upper bounds the condition number of the matrix. Now, in the paper that I'm using as the starting point in this discussion, there is also somewhat hidden assumption that the matrix is positive semi-definite, and then all the eigenvalues lie in this interval. Okay. So in particular, so that the spectrum of the matrix is all contained between 1 over kappa, where kappa is the condition number, and upper bounded by 1. And so for the description that we give here in these notes, just keep this in mind, that this algorithm is not entirely complete. It really only works if you assume that all the eigenvalues of the matrix lie in this interval. But as I mentioned, this algorithm is the easiest one to explain and to understand, to make sure we understand what are the main ideas to construct a quantum linear system solver. This is not a restriction in reality. In fact, this issue has been thoroughly explored and solved in subsequent papers. So in fact, what you would generally assume in, let's say, modern quantum linear systems solvers is that this appears to be a top. Is that the spectrum of the matrix is in this union of intervals. So why is this union of intervals? Because you want the matrix to be invertible. Okay, so if this is 0, you cannot have 0 eigenvalues, otherwise your matrix is not invertible. But you're okay with a matrix that has spectrum in the union of these two intervals. So this is 1 over kappa to 1, and this is minus 1 over kappa to minus 1. Questions here? Okay. So this is what we're going to make as our simplifying assumptions. And now I want to have a look at how the algorithm works. Okay. Actually, why don't we do the following? Why don't we take a break now? Because I don't want to take a break while we discuss the algorithm. It's probably better to do that all in one session. So it's 7:53 my time, so 1:53 Paris time. So why don't we take a break now, and we come back again at 2 p.m. Paris time.
I forgot that for everyone to work on take 2 hours. There's another case called Gazotomy. You can find it on the website. I'll put it on the discussion if people want to share and discuss, like a virtual coffee break, of course. So see you in
6 minutes at this point, yeah. Okay. Okay, I think we can. I think we can restart. All right, so let's dive into the algorithm, and this will be a slow dive. So I want to first give you what is the main idea of the algorithm, and the idea of the algorithm is to decompose the right-hand side vector B into an eigenbasis for the matrix A. And we're going to do this using phase estimation. Once we have decomposed this vector B into an eigenbasis of A, we'll see that computing the inverse actually becomes a lot easier, because at that point, the only thing we need to do is to take the reciprocal of the eigenvalues. And if this sounds too abstract, it's spelled out later on, so we'll go through this slowly. So see, here's the main idea for the algorithm. So I'm going to define some circuit that computes some sort of Hamiltonian evolution. That's why I'm calling it U-Evo. And we want to do phase estimation. So let me just fix the number of qubits over that we use to determine the precision of phase estimation to be some integer number m. I'm not specifying what this integer is for now. We'll pick it later. For now, just assume that you have some number of qubits that you want to use to do phase estimation, and we'll use this phase estimation to decompose the right-hand side vector into an eigenbasis for the matrix A. Okay. So what this circuit does, what this Hamiltonian evolution circuit does, is the following. So it may look like a complicated expression, but let's go through this together. So for every value of k, where k is a m-digit binary string, it applies some matrix exponential where the duration of the simulation is this number k here. So for every value of k, it applies Hamiltonian simulation, but for a different duration, particularly for increasing durations k. Okay. Now, what is this? This expression here is just a projection. So if you think about this classically, this is the same. You're taking column vector times a row vector, right? This is the same as if you write classically, let's say, x transpose. So it's a rank one matrix, and in particular, it's the rank one matrix that projects onto K. So what does this do? Well, the reason we write things in this way here, this simply means do something if the first register has value K and do nothing otherwise, because this times, let's say, some vector j, right? This is going to be equal to k if j equal k, and it's going to be 0 otherwise. Okay, so this thing here, this is simply the control. It tells you when you have the value k in this first register here, do this Hamiltonian evolution for the time specified by k, otherwise it doesn't do it. And then you sum these over all k's, so this tells you exactly for each value of k in the first register, what is the duration of the Hamiltonian simulation that you should apply. And the way this circuit is set up is that if you remember what the circuit for phase estimation looks like from yesterday, this is really set up as a phase estimation circuit. You have Hadamard's at the beginning, you have the inverse quantum Fourier transform at the end of the circuit, and then in this part in the middle, when we discuss phase estimation, here you would have had all these control unitaries. This is where in our previous lectures that we called it, we had something like this, u, and then you had u square, and then you had u to the fourth, and so on and so forth. So this part here takes the role of this controlled circuits. And in particular, it does something similar just because it applies this operation here. And so in some sense, actually not in some sense, it is exactly applying some exponential of some matrix because of this number k here. So this is the circuit that we want to run. And we will run this circuit on the following input. So in the top register is the one that we use to do phase estimation. We start in the state 0 in the same way that we did for phase estimation. And in the bottom register, we start with the right-hand side vector b. This will be our eigenvector. So when we apply phase estimation, in this bottom register, we would put an eigenvector. Now we put the vector b, which is not an eigenvector of the matrix A. I'm aware of that, but we'll see why this works anyways. Any questions so far? Okay. So let's see why this works. Let's see what the circuit does, and let's see what it gives us. Okay. So as I mentioned, we want to decompose the right-hand side vector b into an eigenbasis of the matrix A. So let me, give labels to the elements of this eigenbasis. And so let's say that there are some. So A is a matrix of size, 2 to the n. It's a 2 to the n by 2 to the n matrix. And so it's going to have at most 2 to the n eigenvalues and eigenvectors. Let me call the eigenvectors of the matrix with this notation here. They'll be called psi h, for h that ranges from 0 to the n minus 1. And these are going to be the corresponding eigenvalues. Okay, so the matrix A has these eigenpairs. So these are the eigenvalues and the eigenvectors. So we said that we pick some number m, some integer m, to determine the number of qubits of precision that we need. And so, because we can pick this integer, let's assume that we pick the number of bits of precision for phase estimation in such a way that each eigenvalue can be expressed exactly on that many qubits. Okay, so in some sense, so we said, the eigenvalues are this lambda h. Ensure that the number of digits of precision that we use for phase estimation is large enough that each one of these eigenvalues, lambda h, can be represented exactly in that many digits. Okay. Any questions so far? So for now, I'm giving names to some orthonormal eigenbases of A. And notice that, we assume that A is a Hermitian matrix, so this exists. There is always such a orthonormal basis of eigenvectors. Okay, so what I want to do next is that we're going to use, again, the fact that all quantum operations are linear operations. And so we'll start by looking at the effect of this circuit on only one of the eigenvectors. Okay, so in particular, I'm going to run this circuit, and as the input of the circuit, rather than having B, let's just assume for now that we put size 0 here in the bottom register. Okay, we're going to run the algorithm using B rather than size 0 there, but for now I just want to use the fact that the circuit is linear. So let's just look at what happens if I put size 0 in as the input for the bottom part of the circuit, and then we use linearity and look at the effect of what the circuit does on B, because B is going to be a linear combination of eigenvectors of A. Okay. Any question on this? So recall what the circuit does. This is the circuit. So it starts by applying Hadamard's everywhere. So now we're doing this, right? So you have 0 as the input at the top, and you have size 0 at the bottom. So the first operation we apply is Hadamard gate in the top qubit lines. Hadamard gates create the uniform superposition. So in the first part of the quantum state, we have this uniform superposition over all the possible busy states K on m digits. And the bottom part of the circuit is still size 0. We didn't do anything to it. What we do next is that we apply this control evolution circuit that applies Hamiltonian simulation. So this is exactly this guy here. Okay. So let's see what's the effect of this. So, okay, actually, let me go back one slide. Remember that if I apply this, because of the way this is expressed, right? This is the control part of the circuit. It tells you do something when you have the value K in the input register and do nothing otherwise. So in particular, all those, K, all the terms of this form here, they're going to react with these guys here, and they're going to be non-zero only where the two values of K are the same. So when you apply this evolution circuit onto the state, that contains a superposition here over K, what you get is that whenever the top register contains the string K, then you apply Hamiltonian, the matrix exponential for the corresponding value of duration K. Just in the same way that we saw in the previous slide. Okay. But now I want you to think for a second what happens when we apply this matrix exponential onto the vector psi 0. Remember that by definition, these guys here, these are eigenvectors of the matrix A, okay? And if you apply a matrix exponential onto a vector that is an eigenvector for that matrix, what you get back is simply the exponential of the eigenvalue. So in particular, if psi 0 is an eigenvector of A with eigenvalue lambda 0, then psi 0 is an eigenvector of e to the, say, A with eigenvector e to the lambda 0. Okay? So if I have an eigenvector for a matrix with some eigenvalue, and then this eigenvector is also an eigenvector for the matrix exponential of that matrix, and to get the corresponding eigenvalue, I just need to take the exponential of the corresponding eigenvalue. So here, we're applying this matrix exponential, but lambda 0 is an eigenvector of A. Therefore, when you apply this matrix exponential, what you get is that lambda 0 stays the same. It's still an eigenvalue. So what you get back is just a multiplication factor, the eigenvalue. And what the corresponding eigenvalue is just this guy here. It's the exponential of the eigenvalue corresponding to psi 0. Any question on this? This is sort of a crucial step. And okay, then what I'm going to do next is that I'm simply going to move this factor from here. I'm just going to write it to multiply the first register. This is simply, just a rewriting of exactly the same expression. Remember, whenever you have tensor product, if there's a scalar multiple, you can move that scalar wherever you want in the expression. Okay? So what this is telling me, in short, is that if I apply, after I apply the evolution circuit that computes the matrix exponential onto this state that is initialized with a superposition and then the first eigenvector of A, what I get back is that the bottom register stays in the state corresponding to the eigenvector, and in the top register, I get this phase factor where the eigenvalue lambda 0 appears. Any question? Okay. And now remember, so I'll go back 1 second to the circuit. So what do we do next? We apply the inverse quantum Fourier transform. So let's do that. Inverse quantum Fourier transform. Inverse quantum Fourier transform only on the top part of the circuit. Bottom part of the circuit, we don't do anything. So that's why we write here, that there is an identity. So what happens if we apply the quantum Fourier transform onto the top qubit line? So top qubit lines mean we're applying quantum Fourier transform onto this part of the state. But now, if you look at what we have in this register, this is exactly a Fourier state, okay? This is the Fourier state corresponding to the number lambda 0. Okay, we have exactly all the components of the Fourier state. So remember, quantum Fourier transform performs this mapping. Summation j e to the 2 pi I j k over 2 to the m times j. Right, this is what the quantum Fourier transform does. And so here we already have a state of this form, which means if we apply the inverse Fourier transform, then we get back, this guy. And specifically, this guy here, well, I guess I chose my indices poorly. This should have been. Yeah, and in this expression here, this k takes the role of j here. Sorry, I should have written it the other way around. So this is the index that varies, k. This is the one that is fixed. If I apply inverse Fourier transform, I get back the index that is fixed, lambda 0. So exactly this guy here. Any question on this? So as usual, we're doing quantum Fourier transform tricks. Construct a quantum state, construct a Fourier state corresponding to some number that we like, and then apply the inverse Fourier transform so that we get back that number. But the other thing to notice is that in this discussion, there is absolutely nothing special about this eigenvector psi 0. So this same reasoning would apply to any other eigenvector. It would apply to psi 1, it would apply to psi 2. You could write the exact same equations for any one of the eigenvectors. And so now let's use the fact that quantum operations are linear by applying this algorithm to a superposition of the eigenvectors. And more specifically, what superposition? Well, let's just decompose the right-hand side into an eigenbasis of the matrix A. Okay, so remember, we can always do this. So A, here we assume it's a Hermitian matrix. It has a basis of eigenvectors. So if you give me any vector B, there is a way of expressing this vector B as a linear combination of eigenvectors of A. Now, so I'm going to express it as this combination of eigenvectors with coefficients beta. Something to remark here is that I'm not claiming that I know these coefficients beta. I'm just saying they exist. So there is a way of writing B as a combination of eigenvectors of A with some coefficients beta. I don't know these betas, but I know that they exist. So I'm just going to write B in that form. Okay, and now we're going to apply the algorithm. So the way we initially described the algorithm, which is in fact that we apply the algorithm using B in the bottom register, not just size 0. So let's look at what happens. So now we're applying the algorithm. You know, this is the superposition because of the Hadamard's. This was the controlled evolution circuit, and then the inverse quantum Fourier transform. This is exactly the circuit that we showed earlier. And now in my bottom register, I have the right-hand side vector B. So I'm going to express the right-hand side vector B in terms of the eigenbases. So I'm rewriting B with this, right? This is equality. These two are equal. Okay. And then remember, everything is linear. So what am I doing next? So this summation, let me do this. This summation with the beta coefficients, I'm just gonna collect it and take it outside. Okay, I can do this, everything is linear. So let me just put the summation as the first term of this expression. And then I apply the circuit now here. So here I have these eigenvectors, psi h, but we have seen what is the effect of the circuit above here. So if I delete this, now this part is exactly the same as this part. Okay. The only difference is that, you know, now I have lambda h rather than lambda 0. Sorry, I have psi h rather than psi 0, but you know, it's exactly the same circuit, and this reasoning works for every eigenvector. So the circuit has the same effect. And in particular, what this circuit will do is that it will write the eigenvalue lambda h in the first register. Okay, and of course, you know, you still get this summation here. The summation over the bh over the beta h comes from this part. And in the second register, you still get psi h in exactly the same way that you had psi 0 here at the top. I'll give you a bit of time to look at this and think about it, and I'll take questions in the meantime.
I have a question.
Yes, yes.
Probably more than one question actually, but I'll try to ask both of them. So you initialize the bottom part with B, right?
Yes.
but B not necessarily written as combination of the psi H. So it's just, this is the part I don't get. If you just initialize with B, and in the end you get in the register this beta H and lambda H and this psi H as output, this is the part I don't get. So
I understand. I think I understand the question. Now, the thing to remember is that, so I'm not claiming that I know this coefficient beta. Okay. I'm claiming simply that this is true. So this expression that beta is equal to some linear combination of the eigenvectors of A, this is true because these eigenvectors form a basis.
sure, but we don't know the eigenvectors either.
I agree. So we don't know the eigenvectors and we don't know the coefficients of this linear combination. But what's important to try to understand here is that this does not matter. The algorithm is not requiring me to input these eigenvectors and these eigenbases. I am simply writing beta in terms of this combination of eigenvectors just to understand what the algorithm is doing. Why am I doing that? Because, sorry, I need to go back. So what we saw here is the effect of the circuit on a single eigenvector. So we know what the algorithm does on one eigenvector. Remember that if I know the effect of the algorithm of an eigenvector, everything is a linear map. If I know the effect of the algorithm on each eigenvector, I have fully specified what the algorithm does because I have specified the effect of a linear map on a basis. So this tells me everything. And so this trick of writing everything in terms of the eigenvectors is purely for me to understand what the algorithm is doing. The algorithm doesn't require to know what these eigenvectors are and what these coefficients are. But we know what the effect of the eigenvectors is, so this fully specifies the algorithm, and I'm perfectly allowed to decompose the algorithm just to look at the effect on each one of the eigenvectors. In some sense, it's precisely, it's the power of superposition that kicks in here. So everything is linear. If I input a superposition of things, it will act on each one of the terms of the superposition. This is true even if I don't know how to decompose the initial state. It's just that there is a way of writing the state in this form, and therefore this is exactly what the algorithm is doing.
So we are proving the correctness of the algorithm, or the
You're proving correctness.
Yeah. Okay, thank you.
Yeah. And something interesting that is happening here that we didn't see yesterday when we discussed phase estimation is that we're doing phase estimation simultaneously on all of the eigenvectors. In particular, yesterday we saw phase estimation as the problem of, you give me a matrix, you give me one eigenvector, compute the eigenvalue. But this is the quantum world, so everything is linear. So if I can do this on one eigenvector, I can do this on a superposition of eigenvectors. And this is exactly what is happening here. This vector B can be written as a combination of eigenvectors. So if I apply phase estimation, it will apply phase estimation simultaneously on each one of the eigenvectors. And that's why you get the eigenvalues in the first register as the output of phase estimation. And by the way, this is a, this is the first question that comes up when you look at this the first time. I don't know this coefficients beta, and I don't know this eigenvector psi. Why does this work? And then it can take a bit of time to convince yourself that this doesn't matter. I'm just looking at the effect of the algorithm on each one of the eigenvectors, and then by linearity, if I know the effect on each eigenvector, then I have fully specified the algorithm, and then this is the only thing that can happen. Okay. So here, this is what we have in the end. So we have, after we apply this circuit, we have this combination of eigenvectors with coefficients beta h. And in the first register, we have a description of each of the eigenvalues of the matrix A. Okay, so we're getting close to the end of the algorithm. So in the previous slide, this is what we had. Now, what I want to do next is that, my end goal is going to be the following. So I have a description of the eigenvalues here in this register. I want to somehow transform these eigenvalues and move them from this register here to here. I want them to divide this beta h. Why do I want to do this? I'll show you in the next slide, because this gives you the solution. For now, just believe me that this will get us exactly to the solution that we want. How am I going to do that? I will do that in the following way. And I'm skipping a bunch of details here, but I want to give you the main idea. So just let me add one extra qubit to my whole calculation. Or just assume now there's one more qubit that was there all along, but so far we always ignored it and didn't do anything with it. And then I'm going to apply some rotation circuit that looks at these values here, the description of the eigenvalues lambda h, and performs a rotation on the last qubit, depending on the value lambda h. Now remember what we discussed yesterday. So when you think of single qubit gates, every single qubit gate can be thought of as some sort of rotation. So rotations are, unitary matrices. It's a very natural way of thinking about quantum operations. So what I want to do here is that I want to rotate this last qubit by an amount that depends on lambda h. And in particular, I want to implement this rotation, right? So I'm calling this a rotation. If you think of a qubit as being described over, this axis, let's say these are my basis elements 0 and 1. My qubit initially starts in the state 0. I want to rotate it a little bit. And the amount of this rotation depends on this eigenvalues lambda h, which I know now. They are in the register. And so in particular, this is the rotation that I want to implement. And so there are some details that I'm skipping. So in particular, you may not be able to do this rotation as it is. In fact, in reality, here there should be some normalization constant here, and there should be some normalization constant here, but we can ignore these details. It doesn't really matter too much for now. Okay, and notice that if
what if lambda, Giacomo?
Yeah.
What if lambda h is 0 or very close to 0? Is that a problem?
Yeah, that would be a problem. Yes. So that's precisely the reason why you need. So, okay. So for this to be a valid rotation, everything, remember, this guy here, this should be a unit vector, right? Everything should be unit vectors. So for everything to be valid, this coefficient here has to be smaller than 1. You can also see this, because of this square root here, right? So the square root of something here needs to be under the square root, I need to have something positive. So in reality, what you need here is a normalization constant, which depends on the smallest eigenvalue. So that in that way, even if some lambda h is very close to 0, the normalization constant is going to be large enough that here I still get something which is, you know, less than 1. But in fact, this is the reason why. So if we go back a few slides, this is precisely the assumption that we had, that the eigenvalues lie within a certain interval that we know. And in fact, we have an upper bound on this condition number. So I need to know what the upper bound on the condition number is, so that I know that every one of my eigenvalues is in this interval, 1 over k to 1. And if I know this, I can properly set the normalization constant to ensure that this is a valid rotation. This is precisely the reason that you need this, so that even if there are small eigenvalues, I know how small they can be, and I can make sure everything is okay. But so for simplicity, let's just assume everything works out. So I'm going to ignore the normalization constant and just write everything in this form. And I'm not going to give the details on how you do these rotations, but you can sort of imagine this is not going to be too hard in some sense. So rotations is the most natural operation you do on a qubit, and the only difference is that here, rather than doing a rotation by a fixed amount, I want to do a rotation that depends on this amount here, on what is written in the first register, but that's also something we can do. You just need to do this as a controlled rotation. So rather than being an unconditional rotation, this is a conditional rotation that looks at the first register and based on that amount rotates the last qubit. Other questions? Okay. So we're really close to the end of the algorithm now. In fact, this is the end of the algorithm. I just need to convince you that once we have this, we basically have the solution. Okay, so what are we doing next? So let's summarize. So this part is the first circuit that we discussed. This is what applies to phase estimation and determines the eigendecomposition of B. Then we said add 1 qubit. We added this qubit here at the bottom and perform these rotations. And overall, this creates this state. Okay, so this was our discussion so far. Now, at this point, we're basically at the end. There is one more step that we need that I'm not going to discuss in detail, but there are more details on this in the lecture notes. So you will also need a cleanup phase. And what I mean by this is the fact that you will need to ensure that you clean up the first register, the register that you use to do phase estimation, to ensure that you don't leave any garbage in the computation. The reason you do this is because of something that I actually wrote in the lecture notes for the first class, but we didn't have time to discuss. So if you have time, if you had time to go through the lecture notes, I did mention and I made some examples about this principle of implicit measurement, which is something that tells you that in the quantum world, you should ensure that you clean up your garbage. If you didn't have time to look at it, that's okay. You don't have to worry about it now. You can look at it later, but just believe me that you will need to clean up things a bit just to make sure you don't leave garbage during your computation. So overall, if we do this, let's say we do this cleanup to ensure there's no garbage, what do we have left now? Okay, so remember there are 3 registers here, okay? So first register is the one that contained the eigenvalues, but now we reset this guy. So now this register is going to be empty and we can ignore it. There is a second register. This is the register that we use that initially contained the vector b, and now we expressed it in terms of an eigen decomposition of b. This is now what you have in the second register, assuming that you observe a 1 in the last register. Actually, let me do this again. Let me do this again, because I don't think I explained this well enough. So this is this is the final expression of the circuit, and now I'm saying the following. So ignore this guy here. Pretend it doesn't exist. We just erase whatever was there. And now, suppose you do a measurement on the last qubit, and suppose you observe 1 in the last qubit. Okay? Remember, if I perform a measurement, then my quantum state collapses to everything which is compatible with my measure, with the outcome of the measurement. So if I observe 1, then it means that this disappears from the quantum state, and what is left is just this guy here multiplied by the rest. Okay? And so these blocks, these 3 blocks, are the only things that are left if I observe 1 in the last register when I perform a measurement. And so in particular, I'm simply rewriting these 3 blocks in this way here. Look at what happens. So you have summation h over h of beta h divided by lambda h. These are all coefficients. I can move them wherever I want. They're scalars. Times the eigenvectors, and there is a 1 in the last register. Okay? Again, I'll give you some time, and I'll take questions in the meantime. So notice that I'm not saying that you always have a 1 in the last register. I'm saying perform a measurement on the last qubit, and let's assume that you observe 1 as the outcome of the measurement. So this will only happen with some probability. That's okay. We'll take care of that later. But for now, let's just assume that you perform this measurement and you observe 1. So that we can focus on the part of the quantum state that we like, because what I want to show you next is exactly that if you observe a 1 in this last register, then this register here contains the solution. This is the solution of the linear system. If you did not observe 1 in the last register, then your algorithm failed. Okay. So now let's convince ourselves that if you observe 1, you have the solution. And I think we'll take a break after this. So we ignore this state here, okay? So the state that we use for phase estimation, we're now ignoring it. We just erased any garbage. It doesn't exist anymore for us. So this is the state we have left. And then we also said, assume that you perform a measurement and you observe 1. So this is the only part that is left. This guy disappears. And so what we saw in the previous slide is that when this happens, the second register contains this expression, summation over h, beta h over lambda h times psi h. And then let's see why this is exactly the solution of the linear system. So remember that we decomposed. So we define lambda h, psi h to be the eigenpairs for the matrix A, okay? So A can be expressed as a combination of the corresponding rank 1 projectors. Right, just to make things just to write things in a more familiar notation, if everything was, you know, classical and we were writing things classically, you would write this as summation h lambda h x h times x h transpose, where these xh are the eigenvectors. So, you know, each one of these guys here, this is a rank 1 matrix. It's the rank 1 matrix that projects onto one of the eigenvectors of A. And we know by our assumption on A that I can always express A as this summation of rank 1 matrices, each one corresponding to an eigenvector, and you just multiply it by the corresponding eigenvector. So this is exactly what we have here. I'm just expressing A as a summation of rank 1 matrices, each one projects onto one of the eigenvectors. So, but once you have A written in this form, then finding the inverse of the matrix is trivial. The inverse of the matrix is just this guy here, where you take the reciprocal of the eigenvalue. Okay? And you can easily convince yourself of this fact if you just, you know, if you write A minus 1 times A, then, you know, this guy cancels out with this guy and you get a 1. And then what you get in the end is just a summation over all these projectors. And this will be exactly the identity. So this is the inverse. Okay? If that is the inverse, let's look at what the solution of the linear system looks like. So if I now write a to the minus 1b, which is my solution, this is a to the minus 1. It's the expression we just found. This is b. We just express b in terms of a linear combination of eigenvectors with some weights beta h that I still don't know. And then if you carry out this operation, you know, remember these guys, they're all mutually orthogonal. So this expression is going to be non-zero only when lambda h here is multiplied by the corresponding lambda h on the left-hand side. Otherwise, all these inner products are 0. And so what you get left is exactly summation over h, beta h over lambda h times the eigenvectors psi h. And so this, you know, this is the expression that we found for the solution of the linear system. And it's also exactly what we have in the output register for the algorithm. Although, as I mentioned, you know, I did some simplifications here. There were some normalization constants that I ignored. So, you know, there will have to be some other terms here and there, but this is the general idea. Any question?
So I have a question.
Yeah.
That probably is a trivial one, but just to be just gets a bit hard to get into the quantum field, let's say. And what happens if I measure this this quantum bit here?
Mm-hmm.
So I can just compute that, right? I cannot read all the components of the solution of the system. Am I
You
wrong?
cannot read the components of the solution of the system.
So I can just compute that. I know that
in
that register I have my result, but I cannot access it.
You are 100% correct. I never said that this gives you as the output, each component of the solution. What I'm telling you is simply the following thing. I have computed a quantum state that contains the solution. So the quantum state is the encoding of the solution. Each coefficient of the quantum state corresponds to a coefficient of the solution. I'm not saying you can read it.
No, of course. I was just to see if I was right. Thanks.
You are 100% correct. Okay. Other questions? Okay, so I think this is a good time to take a break. So now it's 8:57. Let's take, yeah, I think the next part is not as heavy. So why don't we take a break until 9:10 my time. So that would be 12 minutes. Let's take a 12-minute break, okay? Yeah, break until, yes.
Translation from Europe, yeah.
Excuse me? I'll be back in a few minutes. Okay. Okay. Last part. Any questions before we start? Okay. So there are two things left in this class. Actually, it shouldn't take too long. So the first one is that I want to discuss just a little bit some of the parts that we swept under the rug in the discussion of the algorithm. And again, I'm not going to give details, but just to give you a sense of what other things one should keep in mind. And then I want to do a running time analysis of the algorithm. And finally, I want to talk about some other tasks relevant for optimization that can be done using Hamiltonian simulation. So let's first discuss some of the details that we overlooked in the algorithm. One thing that we did from the very beginning is that we just assumed that when we're doing phase estimation, we're using some number of bits of precision m that is sufficient to represent all eigenvalues. So in particular, this is equivalent to saying we just assume that if you multiply each eigenvalue by 2 to the m, you get exactly an integer number. In fact, this is very similar to what we did yesterday when we discussed phase estimation. It's a lot easier to just look at the case in which you assume that everything can be represented exactly in finite precision. And then in reality, that may not be the case, but this does not create too many problems. It makes the analysis a little bit more complicated, but in general, the point is that everything we're doing is, again, continuous transformation. So as long as your input is close enough to this number here, so as long as the eigenvalues, as long as 2 to the m times lambda h is close enough to being an integer, then you will get some small error that will decrease your probability of success a little bit, but this error is not going to be very large. So as long as you choose m to be sufficiently large that you can represent most of the enough of the bits of precision of the eigenvalues, then you're fine. And there are some details on this in the lecture notes if you're interested, but it's not really necessary for what we'll do afterwards here. There's also the fact that I sort of ignored numerical instabilities that might show up when you try to compute the reciprocal of the eigenvalues. This, as you can imagine, is not entirely straightforward. In some sense, what I'm trying to say is that we're computing these eigenvalues with some precision. So there is going to be some error introduced by phase estimation because we're only using a finite number of bits of precision. But if some eigenvalue is very small, let's say some eigenvalue is roughly of the order of 1 over kappa, the conditional number, then a small relative error in the computation of this eigenvalue introduces a large absolute error when you take the reciprocal here. Okay, so in particular, the inverse of some eigenvalue, we said this eigenvalue is initially of the order 1 over kappa. If you take the reciprocal, it would be roughly of the order kappa. And then if you have a small relative error in this estimation, now kappa could be potentially large, and then your small relative error could still be a large absolute error. And this will make your algorithm overall less precise. And to deal with this, one has to be a little bit careful in the way that the map to compute the reciprocal is implemented. And as I also mentioned earlier, there is this fact that we need to choose a normalization constant appropriately. Otherwise, some of the operations that we saw earlier are not well defined. But again, none of this changes the main idea of the algorithm. And if you're interested, there are some more details in the lecture notes. And in fact, even some of the details in the lecture notes are sort of outdated. I wrote some of these lecture notes before some of the recent papers that are dealing with some of these issues in a cleaner way. Okay, so let's look at the complexity of this algorithm. So I mentioned that one of the assumptions of the algorithm is that we have access to some quantum circuits that appropriately describe the input data. So in particular, I mentioned that we need a circuit that prepares the state encoding the right-hand side, B, and then we'll need some circuit that describes the entries of the matrix. So let me call TB the cost of the circuit that implements that constructs the right-hand side vector B. So here the cost would be number of gates. How many gates does this circuit have? Okay. So what is the cost for the algorithm? We need to do two main things in this algorithm. We need to apply phase estimation, and we know that if I'm using m bits of precision to perform phase estimation, the cost of phase estimation will roughly be m squared. We also need to perform the controlled evolution. So this guy here. And I'll go back a few more slides. Remember that what this guy applies is this map. And this contains exactly Hamiltonian simulation, the computation of a matrix exponential. So what is the cost of computing this matrix exponential? As I mentioned, the cost of Hamiltonian simulation depends on the input model. But if you take some of the most efficient algorithms for Hamiltonian simulation, if I want to run Hamiltonian simulation of let's say e to the minus I a t0, the cost of a quantum algorithm to do so is given by this expression here. So it depends on three things. It depends on the time for which you want to, the duration of the Hamiltonian simulation. You can think of this as simply, what is the constant in front of the matrix in the exponent? It depends on the time TA, which is the complexity of a description of the matrix. So in the sparse model, where we say you just need to give the map that describes the non-zero elements and their values, this TA is exactly the number of gates that it takes you to implement those maps that we described earlier. So one map that tells you the position of the non-zero elements, and one map that tells you the value of the non-zero elements. And finally, it depends on this sparsity parameter S, which is the maximum number of non-zeros in a row of A. Now, something that I'm using here, and that's why I have this remark, I'll use this expression also later on in the second class for today. Whenever you see something indicated as big O tilde, so the big O with a tilde on top, what this means is that it's ignoring everything that appears with a logarithm in front. Okay, so if you have any expression that has some logarithm, then if you want to write this expression in the O tilde notation, everything that appears in a logarithm, you can just ignore it. And the reason this notation is used very frequently is because logarithms grow very, very slowly. So in general, when you're looking at the complexity of the algorithm, it can be convenient to ignore factors that grow only logarithmically so that you don't have to keep track of them in the running time expression. And also in practice, they will not make a big difference in general. You know, it's an approximation, but you're only ignoring terms that grow very, very slowly. So generally, they don't matter too much. Now, to look at the final running time of this algorithm, so we need to do two things. So the algorithm starts with the bottom register that is in the state B. Okay. Remember, we started the algorithm, we assume that the bottom register contains the state encoding the right-hand side. So in the running time expression, there will be the time that it takes, so the gate complexity of preparing the right-hand side vector. That's expected. And the other term that appears in the running time analysis is the time for the Hamiltonian simulation. Now, to know the time for Hamiltonian simulation, we need to know how do we choose the time duration parameter. And this is part of the details that we swept under the rug. So I'm not going to give details on this, but just believe me that you need to choose this parameter to be of the order of kappa, the condition number, over epsilon, where epsilon is your precision parameter. So this gives you a running time expression like this. So it's big O tilde of TB, the time to construct the right-hand side vector, plus kappa times the sparsity parameter times the complexity to describe the matrix divided by epsilon. And so notice once again, the size of the matrix does not explicitly appear in this running time expression. So this is an oracle complexity. It's telling you the complexity in terms of the cost of the circuit to prepare the right-hand side vector and the circuit to prepare the matrix to describe the matrix A. But in principle, the size of the matrix does not appear directly in the running time expression. The size of the matrix can only appear indirectly as part of, for example, TA. And another thing to notice is that so far, our discussion so far is based on the assumption that, let me go back. Everything we discussed so far is based on the assumption that you observe 1 in the last register. Okay. So we saw that you get the correct answer if you perform a measurement in the last register and you see 1 as the outcome. But of course, this is not necessarily the case. So, this last register contains a superposition of 0 and 1. So if you perform a measurement, you might observe 0, you might observe 1. So what's the probability that we observe 1? So This is also part of the details that we swept under the rug, but one can show that the probability that we observe a 1 in the last register, which is what we need to get the correct solution, is big O of 1 over kappa squared. And in fact, this comes basically directly from the fact that, as I mentioned, I'll go back a few slides again. You know, here there was supposed to be a normalization constant. And remember, I mentioned that we had this discussion regarding what happens with small eigenvalues. And I said, you need to pick a normalization constant, which is roughly of the order of 1 over the condition number, to ensure that even if you have small eigenvalues, this is a well-defined expression. So directly related to this, as a consequence of this, the probability that we observe 1 in the last register is 1 over kappa squared. So in principle, so the probability of success is 1 over kappa squared. Let me write it here. So if I want to get the solution, so the expected number of times that I need to run this algorithm to get the solution of the linear system is 1 over the probability of success. Probability of success is 1 over kappa squared. So this means I would need to run the algorithm kappa squared times in expectation to get the right solution. However, what I also mentioned yesterday when we discussed Grover search is that Grover search can be generalized, and it's generally called amplitude amplification. So if you have an algorithm that succeeds with probability P, using amplitude amplification, you only need to run it an expected number of times, 1 over the square root of P. And so by virtue of this fact, we gain a quadratic speedup, and so you only need to run the algorithm kappa times in expectation to get the correct solution. This is a direct application of amplitude amplification. And so if you put everything together, this is the running time to run 1 iteration of the algorithm. 1 iteration, so let's say, 1 iteration, I mean 1 full execution of the algorithm. 1 full execution of the algorithm is successful with probability 1 over kappa squared. Using amplitude amplification, we get the correct solution, running the algorithm an expected number of times, which is kappa. So the total running time is this expression multiplied by kappa. And so this is what you get. And so notice some difference with respect to classical algorithms. So first of all, the condition number here appears directly in the running time. This is also true of some classical algorithms for linear systems. Okay, if you use iterative algorithms for linear system, there are algorithms that have direct dependence on the condition number of the matrix. But not all algorithms depend polynomially on it. There are algorithms that are numerically more stable with respect to the condition number. So in particular, if you look at your standard Gaussian elimination, normally the running time of Gaussian elimination is given as n cubed for an n times n matrix. It's not given in terms of the condition number. And here you have the condition number directly in the running time expression. Then you have the time to construct the right-hand side. And then this other term that depends on the condition number again, some precision, the sparsity of the matrix, S, and then the complexity of describing the entries of the matrix. But again, the size of the matrix is not directly appearing in this running time expression. So if, and that's a big if, but if these two running times TA and TB do not depend on the size of the matrix, then this overall cost does not depend on the size of the matrix. Or, okay, maybe I should rather say, if TA and TB have a number of gates that depends only logarithmically on the size of the matrix, then this expression depends logarithmically on the size of the matrix. And I should also say this is not the fastest algorithm for linear system, quantum algorithm for linear systems. There are better algorithms in the recent literature. Any question on this or anything else? Okay. So how do we deal with non-Hermitian matrices? So far, we assume that the matrix A is Hermitian. What is it not? And for example, this matrix may not even be square. As it turns out, this is actually not difficult to handle. Just rather than working with an eigen decomposition of the matrix, you work with a singular value decomposition of the matrix. So now my matrix A may not be a Hermitian, it may not even be square matrix. I can still express A in terms of its right and left singular vectors. So now express your matrix as a summation of, column vectors times row vector multiplied by the singular values. And you get these guys here, psi h and phi h, directly from the singular value composition of the matrix. And then you just work, so rather than working with the matrix A, you apply the algorithm to the matrix A prime that you construct by putting A in the top right corner and the conjugate transpose of A in the bottom left corner. And in fact, one can show, and it's not difficult to see if you just carry out, matrix vector multiplications to check that this is the case, that this matrix, so first of all, this matrix A prime is Hermitian by construction. If you take its conjugate transpose, you get back the same matrix. And the eigenvalues, sorry, let's use the other one. The non-zero eigenvalues of this matrix are the singular values, are plus or minus the singular values of the singular value decomposition. And there is also an expression for the eigenvectors. So there's going to be these eigenvectors. I'm writing this with a plus minus because here you could have either a plus or a minus. Both cases give you some eigenvectors of the matrix. So again, this is not obvious if you just stare at the matrix. To make this clear, you have to carry out the matrix multiplication. So look at what happens if you compute A prime times, let's say, for example, WH plus. If you do this, then you'll see that these are in fact eigenvectors with eigenvalues that correspond to plus or minus the singular values. There will also be some zero eigenvalues, but we don't really care about that. And then what I'm saying is apply the quantum linear system algorithm to the matrix A prime. Okay. And the input state that we used is the right-hand side vector B. We just added 1 qubit at the beginning, because even in the previous slide, we added 1 qubit everywhere. And now the difference is that rather than expressing B in terms of if it's eigen, in terms of the eigen decomposition of A, we express it in terms of the singular value decomposition. So you express B as a linear combination of singular vectors. And in fact, these guys, psi h, by definition, they're equal to, so is equal to WH plus WH minus. This is true by construction, let's say, right? So if you look here, if you look at this expression, if you add WH plus and WH minus, everything here cancels out and you get left this psi h. And so if you carry out an application of the algorithm on this matrix, A prime, and with this state that I mentioned, that it's not too difficult to see. It takes a little bit to carry out the calculation, but it's not too difficult to see that you get back some state that you can express in this form here. So we do the same trick in some sense, but rather than having eigenvalues, you now get singular values, but you still compute the reciprocal of the singular values, and you put them as, you know, coefficients that multiply these singular vectors. And these guys, lambda h plus minus lambda h minus, sorry, wh plus minus wh minus, we said you can express them as phi h. Okay, for the same reason as before, just look at this expression here. So if you take the difference of two vectors wh, then you get the, if you take the sum, you get the psi h. If you do take the difference, you get the phi h. And exactly in the same way that we showed the correctness of the algorithm for the case where A is Hermitian, then you do the same trick here. So you express A in terms of its singular value decomposition, and then look at the state that you, so what I'm saying is, this is A, this is the solution that you get from the algorithm. And then if you carry out this multiplication, then, you know, this guy and this guy simplifies. These guys and this guy, they're non-zero only when the indices are the same. If they have different indices h, then their inner product is 0. So what you get back is this summation here, which is exactly the right-hand side vector. Not entirely sure why I wrote this twice. And so this means that the vector that you computed is exactly a solution of the system. So the trick here is the following. Your initial matrix A may not be Hermitian. Just work with this symmetrized version of the matrix. this is Hermitian by construction, and then you can apply the algorithm. And what we just showed is that if you apply the algorithm onto this symmetrized matrix, it will give you the answer that you want. So it will give you a solution of the linear system, even if A was not Hermitian. Any question on this? So in other words, the fact that A is Hermitian is not a restriction. You can just drop that assumption. You can have the algorithm works for any matrix A. You just need to be careful. Okay, and then, final remark on this is the fact that this algorithm for linear systems that we discussed relies on Hamiltonian simulation. So you need to be able to compute this matrix exponential. And so the natural input models for this algorithm are the input models that are also natural for Hamiltonian simulation. And so what we discussed here is the case of, we just assume that somebody gives you a sparse description of the matrix, but there are other models that are possible. For example, this block encoding model where the matrix that you want, that you're interested in, is embedded in the top left corner of a unitary matrix that you can construct. And I should also mention the fact that describing the entries of the matrix is not something that comes for free. This has a cost. We'll see some examples in the next class. And so to get quantum speedups, some research works assume that you have a quantum data access in some sense. So you assume to be in some situations where it's easy to give an algorithm to describe the entries of the matrix. But this is not true in general. So what I'm trying to say here is only the fact that the cost of these, what we call TA and TB in our running time analysis, this may not be negligible, and it should be carefully taken into account when you're looking at the viability of using a quantum system for a quantum algorithm for linear systems to give a fast algorithm. So this may not be negligible. In fact, it might be the bottleneck of your algorithm. So you need to consider carefully how long does it take for you to describe the matrix on which you want to apply the linear systems algorithm. Constructing B is also something that doesn't come for free, and there is a general way to do this, but in general, it might depend on the size of the vector. If we have time, we'll discuss this in the next class. Otherwise, you can see this in the lecture. It's very interesting. Any question? Okay. So last thing, I think only a couple of slides. Another application of Hamiltonian simulation. We'll use this in the next class, but I'm just giving you a very high-level overview. Is the construction of Gibbs states. So Gibbs states is a particular type of quantum state that has physical meaning. We don't care about any of that. I can just give you a more high-level definition of what they are and why they're important for us. So first the definition. So you give me some positive semi-definite Hamiltonian. Let's call this A. And a Gibbs state for this Hamiltonian is a block encoding of this matrix. Okay, so remember what block encoding means is that there is some matrix such that this guy appears in the top left corner, and here I have other stuff. I don't know what is, this other stuff, I don't know what it is, I don't even care. If you look at this expression, notice that this is a matrix exponential, and it is normalized. Okay, so you just take this is a matrix exponential, and you have a normalization factor given by the trace of the matrix. So this is not the only way to define Gibbs states, but this is a way, this way makes sense for what we're discussing here in this class. So a more traditional way of looking at them, which is also relevant in many areas of computer science, we'll look at that a little bit in the second class. I'm mentioning this because some of you, depending on which area you work on, might have seen this already. So Gibbs states are also used to encode a certain probability distribution called the Gibbs distribution. And what is the Gibbs distribution? So the Gibbs distribution is a discrete probability distribution. For simplicity, let's define that over binary strings. And the probability of observing some binary string J is given by this expression here. It's an exponential where I'm just looking at the diagonal element in the matrix A corresponding to the index J, right? So this expression here remember, J is a basis state. So this is really just the diagonal element in position J for the matrix A. So if you want to define a Gibbs distribution, you need to give the matrix A. In fact, the only thing that matters in that case is the diagonal. And you need to give some scalar beta. So betas here are just is a given number. And then you can define a probability distribution. This is the Gibbs distribution. Why are Gibbs states interesting for us? So two reasons. So one reason is that they're used to encode Gibbs distributions. Gibbs distributions are very important in some classes of algorithms, for example, Markov chain Monte Carlo algorithms. And there's, in fact, they're ubiquitously used in areas of machine learning and other areas of computer science. They're also used, Gibbs states are also used to encode normalized positive definite matrices. So in particular, for every positive definite matrix, M, there exists some other matrix, B, which in fact is defined as the matrix logarithm of M, such that M is equal to the exponential of B. Okay, so what I'm saying here is M is equal to E to the B. And so what is a Gibbs state? If you look at this, a Gibbs state is a matrix exponential with a normalization factor. And so in particular, what is also true is that we'll see that there are algorithms for semi-definite optimization that use this property to say, well, I only need to look at Gibbs states because for every positive definite matrix M, this positive definite matrix M, or at least a normalization of this matrix, can be encoded as a Gibbs state. And so in some sense, every solution to a semi-definite optimization problem can be represented as a Gibbs state. There is one small caveat. I talked about semi-definite optimization, and here I said these matrices are positive definite. So dealing with eigenvalues that are 0 is difficult for Gibbs states. but we're always going to solve things up to some level of approximation. So there will always be some error epsilon. And so you can just assume that if you're trying to solve an approximate version of the problem, even if the exact solution has some eigenvalue that is 0, you just set it to some very small value that is non-zero. Any question on this? Okay, so here I was defining what these Gibbs states are and trying to convince you why they are interesting. So they encode Gibbs distributions, and Gibbs distributions are used in Markov chain Monte Carlo algorithms. They also encode positive definite matrices. So in some sense, they encode solutions to semi-definite optimization problems. So up to some approximate notion, they encode the solution. So this is why they're interesting. And this is why they're interesting in the quantum world more specifically. There are efficient algorithms to construct Gibbs states. In fact, you can do certain things on Gibbs states on a quantum computer faster than you would be able to do them classically. So in particular, the following is true. The details of this are rather intricate, but we don't need them. I just want to give you a general sense of the results that one can get and why they are important for optimization. So let's say I'm interested in some matrix A, and I have a block encoding of it. So U is a block encoding of A, which means A appears, some scaled version of A appears in the top left corner of the matrix. And then I can construct a block encoding of a Gibbs. So I can construct a Gibbs state for this matrix A using these many applications of the block encoding of A and additional gates. And so let's start going a little bit over the parameters. So this matrix A is n times n, okay? It's an n times n matrix. In this running time expression, have square root of n. But I also have these two scalars, alpha and beta. Alpha is the normalization factor that I have here in the block encoding, and beta is the constant that I have here in the exponent. Now, to make things simple, let's just assume that beta is 1, and I want to construct a matrix exponential. So I want to construct this block encoding of the matrix exponential e minus to the minus a. Okay. So what's the running time to do this? So classically, if I want to do this classically, just doing matrix multiplication for a matrix of this size requires time n to the omega. This is called the matrix multiplication exponent. Without worrying too much about the details, this is something like this. It's big O of n to the 2.37 and blah blah blah, more and more digits. Okay, so this is the time it takes classically just to multiply a matrix of size, two matrices of size, and by n. And so classically, if you want to compute this matrix exponential, at the very least, you need to be able to multiply matrices. Remember how the matrix exponential is defined. So the running time to do this classically, even just ignoring all the error terms and the fact that there are other error terms, is going to be something like this. But in fact, this is also going to depend on the error. But if I want to do the same thing quantumly, using the result that is here on the slide. So what are the parameters? There's going to be square root of n here, right? We said beta is equal to 1 for simplicity. And then there is this normalization factor. And one can show that for a general matrix, this normalization factor can be assumed to be n. So everything multiplies. And so overall, this gives me n to the 1.5. So there is a quantum algorithm that constructs e to the minus a using n to the 1.5 gates and queries to a description of the matrix. So this is a significant improvement over any classical algorithm for matrix exponential. Although I should, remark that the cost of each query to the description of the matrix may not be free. So the number of gates you need to describe each entity of the matrix might be non-negligible, but okay, at least here we're working with something interesting. We're saying this algorithm, the bare minimum that it requires is n to the 1.5 to construct this matrix exponential. And classically, the bare minimum is going to be something more like n to the 2.37, blah, blah, blah. So there is a significant saving in doing certain operations on Gibbs states than any classical algorithm, with respect to any classical algorithm. And so this is one of the reasons that there is a very active research on doing semi-definite optimization with quantum computers, precisely because of these results on Gibbs states and the fact that Gibbs states can be used to encode positive semi-definite matrices. Any question? Okay. So this is where we stop for the first class for today. And the next class will be more of an overview of a lot of recent research on quantum optimization. And so we're going to have a 1 hour break now. I'll stay here online a bit longer in case there are questions. And after that, I'll take a break and go home, make some coffee.
So in a real course, not virtual, certainly there is some person who upload everywhere in the room, and many thanks to Giacomo.
Or maybe they don't, right? You never know.
Perhaps they have the right to do it or not. Yeah.
They have the right to do, yes, yeah.
So is there no question? The break can be taken, of course, without any virtuality. If you want to ask some question to Giacomo, it can be here. If you want to discuss each other, so I will recall and I will get to a place called Gasotown, which is perhaps a funnier place with virtual tables, games, and place to write on a blackboard and so on. There was some question about exercise. Perhaps that can be given if people wants to make some exercise. It would be certainly the last session. Is that? So it's a 1 hour break. See you at 4 o'clock for European hour.
Okay, I'll go make coffee then. See you later.